Have you ever wondered why a guitar string produces different notes, or why sounds sometimes get louder and softer even when the sources are steady? So, today we are going to fully understand standing waves and beats with clear explanations, diagrams in mind, and enough calculations to prepare you for exams and solving this topic. So, by the end of this lesson, standing waves and beats will feel very easy. So let's begin with forced vibrations and resonance. So let's begin. A system undergoes forced vibrations when it is made to vibrate by an external driving force. Now, yeah. So what's there is a system might be vibrating, or a system might be undergoing vibration. But when you apply an external force, that's what we call it's becoming forced vibration there. So now resonance happens when the frequency of the driving force matters, or not matters. For resonance, it happens when the frequency of the driving force matches one of the natural frequencies of the what? Of the system. So when this happens, energy in system is maximum, and the system oscillates with maximum amplitude. This is why bridges, tuning forks, and air columns can vibrate strongly at certain frequencies. So now this happens when the natural frequency of that object and also the frequency of the driving force, it also matches. So this is what is known by forced vibrations and resonance. So resonance is one of the things that can cause a bridge or a structure to collapse when the frequencies match of the system and maybe of the environment. It can cause what? Problems. Now let's go to standing waves. Now standing waves are formed when two waves of the same frequency and amplitude travel in opposite and what? And interfere. So instead of moving forward, the wave pattern appears fixed in space. So that's what it means, standing waves. Key points is standing waves have nodes, points of zero displacement, and amplitudes, points of maximum displacement. So the distance between two adjacent dots is half a wavelength. So what we mean antinodes and nodes is this. So for example, this is a standing wave. As you can see, this is what they mean. Standing waves are formed when two waves, you can see them, they are two waves of the same frequency and amplitude. They have the same amplitude, I assume they have the same amplitude, travel in opposite and interfere. They have interfered. So now what we mean antinode is this point of zero displacement. This is a node. Even here we have a node. Then this point, that's where we have antinode of maximum displacement. Antinode. So we have an antinode here. That's where the antinode is. So whenever you hear antinode and nodes, this is what we mean. Consider so let's talk about standing waves on a straight string. So consider a string of length L fixed at both ends. The wave speed on the string is given by speed is equal to the square root of F, which is tension, then this is mass per unit length. This one, the symbol down here. Now, what's the frequency? We talk about allowed frequency. So, we have this equation which is Fn is equal to Nv over 2L. So, this equation tells us that when n is equal to 1, it gives us the fundamental what? Frequency. Then 2, 3 going up, it's what? Harmonics. So for the first one, for example, you have So this one, n is equal to 1. That's what we mean. And we have the fundamental of first frequency. Then we go, what about the second harmonic? The second harmonic is going to be found like this. So as you can see, it's like there are two waves, like this. So this is n is equal to 2, any length. Then you can also go third harmonic. This is the second harmonic key, fourth harmonic, just like that. But as you can see here, there are a node, antinode, node, and node here again, antinode somewhere here. Yeah. So let's do an example on the same speed and fundamental frequency. So we have been given a string of length 1.2 meters, which is under tension of 48 newtons and has mass per unit length of 0.003 kg per meter. So to find the speed of the string, we're going to use the same formula, which is, we know the tension is 48 over the mass per unit length is 0.0003. We are going to find that when we punch our calculators, we are going to have 126.5 meter per second. So to find the frequency, we use the same formula, which is nv over 2l. Now for this one, n is just 1 because it's just one string. So what we are going to say is nv, what is the speed? 126.5 over, we said over 2l, 2 times length. What is length? 1.2. At the end, we are going to find 52.7 hertz. So that's all about it. So like the third harmonic will be just 3 times this value. The second harmonic 2 times this value. So this is the fundamental frequency, the F1. That's why I said n is equal to 1. If it was F2, second harmonic, we would have said 2 times 126. Let's talk about standing waves in air columns. So what we mean standing waves in air columns, now we are talking about waves in, we're talking about string. What about in things like tubes? For example, musical instruments where you are blowing, e.g. a flute, if you know a flute, a trombone, all those things. Those who have played in an orchestra before or in a band, those instruments where we are blowing. So those are the point where we are standing waves in air columns. This instrument, this is what I was talking about. This is a trombone. So that there are also tubes when you see like this trombone. Now our lesson today is, if the tube is open at both ends, if a tube is open at both ends, then all harmonics are present. The antinodes form at both ends. So what we mean is, for example, we have a tube like this, then as you can see, this tube, it's open at both ends. It's open here, it's open, but when you see this instrument, I'm sure it's just open at one end, which is this bell here. But other instruments like a flute is open at both ends. So now the one that is open at both ends, you should know the formula you are going to use when you are dealing with such. So for this one, all harmonics are present. We mean it is from n is equal to 1, 2, 3, 4, 5. You go up. That's all harmonics are present. And the formula we are using for this one and is Fn is equal to Nv over 2L. The same one, that formula. So when you are finding the frequency for a tube that is open at both ends, you use this formula, which is where L is the length, V is the speed, N is a harmonic. So the fundamental frequency is going to be V over 2L. The second frequency is just going to be V over L because the tools are going to cancel. One thing again that we talked about was antinodes at both ends. As you can see, there is a node here, but here there is an antinode. Even that side is an antinode. So that's all about it. A tube open at both ends. So you should know the formula we are using. if it's open at both ends? What about if it's closed at one end and open at the one end also? Pipe or a tube which is like this, which is closed at one end, we are going to use a formula. F1 is equal to NV over 4L. Notice the difference there, it was over 2L. And another thing is there are only odd harmonics present, which means N is going to be equal to 1, 3, 5, 7. So the fundamental frequency is going to be V over 4L, but the second harmonic is going to be 3V over 4L. So know the formula you are using. So let's try to look at an example. So how are we going to find the frequency? For example, the fundamental frequency, which is the first frequency. We are going to say F1 is equal to NV over 4L, which is, what's the speed? Find the speed, but the speed is 340, so it's going to be 340 over 4 times 0.85, which is equal to 100. So the next harmonic, it will be the third harmonic, which is 3 times 100, which is going to be 300. So that's how we are calculating the calculations in standing waves. Just know the formula we are using when we are dealing with a closed pipe and an open pipe. Just know the formula you are using. Let's go to beats. Now, beats occurs when two waves with slightly different frequencies combine at a fixed point in space. This is an interference effect. The sound waves becomes alternatively loud and soft because the intensity changes periodically with time. So in beats, the calculations we are going to be tackling its beat frequency. So they are going to tell you can calculate the beat frequency. So just as we said, it's when two waves with slightly different frequencies combine. So the beat frequency is the difference between those two waves. So the formula we are going to be using to calculate beat frequency is FB is equal to frequency 2 minus frequency 1. So the value should be positive. So that's all about beat frequency. For example, they can tell you that two turning forks of 256 Hz and 260 Hz are sounded together. So the beat frequency there is the difference between these two waves. I'm going to say beat frequency is equal to 260 minus 256. At the end, the beat frequency is 4 Hz. So this is the difference that's going to be Hz. So what about, they can also ask you, can you find an unknown frequency? For example, if a 440 tuning fork produces 6 beats per second with another fork, the unknown frequency is, so the unknown frequency is going to be found, we just say 440 plus or minus 6. So you're going to find that the frequency is in the range of 434 or when we add the 2, which is 446. So that's all about standing waves and the beats. So if this video helped you, please, if this video helped you understand standing waves and beats, give it a like and share it with a friend and subscribe for more exam forecasting physics lessons. See you in the next video.